Good afternoon, everyone. Welcome back to the second afternoon of IPN 2022. It's our fourth keynote. The speaker is Dr. Xu Lida from Hong Kong Polytechnic University. Dr. Xu is an associate professor at Department of Aeronautical and Aviation Engineering of Hong Kong Polytechnic University. He is a layman and endowed young scholar in aerospace navigation. He received the bachelor degree and the PhD degree in aeronautics and astronautics from National Cheng Kung University, Taiwan, in 2007 and 2013. He was a visiting researcher with the Faculty of Engineering, University of London, and Tokyo University of Marine Science and Technology in 2012 and 2013, respectively. He is also an associate fellow in the Royal Institute of Navigation. Today, he will give us a keynote report on navigation using graph optimization, a case study of a smartphone user from urban canyon to indoor area. Yesterday, it is reported that our keynote report reached several thousand visits from the live broadcast platform. We look forward to new breakthrough today. Okay. Let's welcome Dr. Xu to give us a report. Let's enjoy it.
Thank you, Dr. Wei, and thank you for inviting me to the talk. So the slide and the voice are good?
Yeah, it's perfect.
Okay, thank you. So hello everyone, so welcome to my talk. First of all, I would like to thank the IPIN 2022 committee invite me to give this talk. My talk is about navigation using graph optimization. Essentially, I'm trying to achieve a seamless positioning using graph optimizations. So I'm also come from the navigation field. I'm frequently join Institute of Navigation conferences, and my expertise is in urban navigations. Right. So considering one example of doing seamless positioning for urban life, which is like myself, like every day I walk on the street, relative open street to the subway stations. Then I walk into the stations and I transporting on the subway trains. Then I walk in the urban area to my office. This is my everyday life. But the positioning are not so much satisfactory in my smartphone. But in fact, our smartphone already provide lots of different sensors for navigations. For example, radio signals, we have GNSS, we have cell signals, we have Wi-Fi. And for inertial sensors, we have gyroscope, we have accelerometer to help us to achieve a PDR. And we also have camera and LiDAR to help us to achieve LiDAR odometry or visual odometries. And recently, people using map a lot, and the map can be regarded as another sensors. By integrating this map with other sensors, we can come up with different positioning approach like Wi-Fi fingerprint. We can do VPS, visual positioning system, by combining with the beams, combining with the beams or visual features in the map. Or we can do magnetic field matchings or even correct our barometric altimeters. And with 3D city models, we can even do 3D image GNSS. We have a bunch of different approaches in our smartphone to provide us positioning. However, we still need a filter or an optimizer to integrate all different positioning methods. When we talk about integrations, that the people look at all these different technology mentioned by different experts already, and how we usually integrate together is using Bison filter. Basically, it's an EKF or a particle filter to come up with integrated positioning result. Now I'm borrowing one slide from Dr. John Rockey, who is our ex-president of Institute of Navigation US. He mentioned that what is the problem for the integrated positionings? Is it that fewer sensors is always better than more sensors and many sensors? in terms of the resource management, you will believe that, okay, so we have more sensors, so accuracy should definitely increase, robustness should definitely increase, the availability should definitely increase. But as a navigation engineers, we often experience something different. We know that complicated noise and error, non-Gaussian error, make it very difficult to turn the filter, and the filter convergence times require longer when new sensors are introduced. So make a lot of different challenge for integrations, especially for common filter. But common filter has been dominating our navigation algorithm as a sensor fusion algorithms since 1960s. So this is our classic equation. You can see this is the propagation, and this is the update, the two-step. It is very popular because of the two reasons. It can achieve the optimal performance under certain assumption. What assumption I will talk about in a second. And because it's a recursive based filter, so it is very computationally efficient. So they have been dominating since 1960, even today. But what I argue here is that with the development of semiconductors, there's more transistors in one chip, meaning our computation load is stronger every day. So it might be a time for us to consider some new filter. Let's looking at estimation theory, maxima of posterior estimations, okay, which is also common filter, is the basic for common filter. Looking at this network here, the X here, meaning the state vector, the position of the user you want to estimate. U here is the propagation vector. Z here is the measurement vectors. Could be PDR, could be Wi-Fi. We want to achieve a maxima of posterior estimate, meaning that we're trying to find a set. Here we say a set of state. The set meaning like from the epoch 0 all the way to the epoch k. All state in the all time domains need to be considered. And we need to find a posterior probability of the set of state that consider the conditions of the measurements and the input. Might find out a state of X, making this biggest. This is the goal for MAP. So we can decouple this posterior probability by Bayesian theory. We can become a joint probability of likelihood. It can be a priori probability and multiply the joint probability of propagation. I say joint here because it's multiple time domain K here. And how common filter is an NAP? How common filter coming from an NAP? We all know about common filter is looking at the two slides, which is the current epoch K and the previous epoch of K-1, and also consider the current epoch K of Z, which is the measurement update, call it likelihood, and the priori probability of K- here. So the first assumption common filter adopt is a first order of Markov. First order of Markov meaning that all the previous epoch from K-2, all the previous epoch, all the way to 0, all these informations can be represented by the previous epoch data, which is K-1. In the other word, K-1 already include all the information we're trying to have from epoch 0 to K-1. Okay, this is first order of Markov. By doing so, that we know that our priori probability can become a propagation probability multiplied by previous epoch of posterior probability. And then with the measurement update, our priori probability then multiplied with our likelihood, then you got a current epoch of posteriors. This is what the first order of Markov do. And the second assumption we make, we do the modeling of the system and we assume that the noise are randomly Gaussian. So when we see this one, we can see our propagation probability now from P, the green one, become an F model. And the orange one, this P, Z in condition of K, become this H. And if it's a Gaussian, then we can derive that this propagation, a classic propagation and classic update is actually an NAP. It is actually an NAP estimate. But how? So I borrow a few equations from Dr. Z Chen from New York University from this paper here. He's trying to prove that common filter is basically a MAP estimate. So sorry, I didn't change the notation here, but the color here meaning the same thing. The red still a posterior. The orange here is a likelihood, and this is priori probability. Okay, so based on the first assumptions that we have a system model. So this probability here, we have a system model GX, and this V here become is a Gaussian. Then the expectation is G of X, and this is the covariance. So the likelihood will looking like this one. And we do the same for the priori probability. We have a model here for the propagations, F. And because it's a Gaussian, so its expectation can be like this, and its covariance could be like this. And the priori probability is looking like the blue box over here. So we're trying to compute the posterior one, which is making this one to here and making this one to here. So this become the posterior probability that we have. So we're trying to find a maxima posterior probability, meaning like we're trying to find a probability. We're trying to find a probability that have maxima. So when we're trying to find this, we need to find a slope that is 0. So we do the partial differential of this one. We do the partial differential of this one. Partial differential according to the state. Then when we find the partial differential equals to 0, which is this point, and this is our MAP estimate. Okay, by these equations that we're trying to derive, you can go to the paper to refer the detailed processes. The result that you find will be this MAP estimates is equals to the previous epoch's propagations and common field again with your measurement innovations. So it can be proved common filter is an MAP. It is optimal. But what's the problem? What's the challenges? So in the past few days, we see that multi-pass and N-loss are actually a very big challenge for indoor positioning because the extra traveling distance and making your noise become very complicated, and your positioning result can even become a non-Gaussian distributed. So this is a positioning result that we record in urban Kenya with a lot of multi-pass and N-loss for GNSS, and this is the positioning result. As you can see, it's clearly not a Gaussian distributed positioning errors, and that will impose problems for common filter because it already violates the assumption that we made. So how it theoretically, if looking at this a violation, how does it affect the common filter? We know that EKF apply two assumptions. One is the first order of Markov chain. The second one is Gaussian random noises. And the first of the Markov chains meaning that it's the recursive filters. So when your noise is non-Gaussian distributed, and how will it affect this recursive filter is like this. If we consider one epoch of k-2, then you know that your propagation probabilities and your likelihood are both non-Gaussian, so they are using light gray shadow here. Then during your recursive processes, then your updated posterior is already affected. If you consider next epoch k-1, and again, this affected the previous epoch of posteriors, again, biased by these noises on non-Gaussian distributed probability again, then your posteriors has a problem again. Let's say if you come to the current epoch of k, then you have cleaned, you have a clean measurement, so P propagation and P likelihood here are clean. But because your previous posterior probability already affected, so even you got a good measurements, your posterior probability estimate in this epoch will not be good. This is why our EKF doesn't performing really well in our synthesis positioning in the sensor fusion now. So what other filter can do something about these challenges? We know that the common filter apply these two assumptions, and we know the recursive features making it quite difficult. So how about we delete these assumptions, and we want to consider all of the state across to the times for estimations. And this one of this kind is called vector graph optimization, which is what I introduce in the next page. So vector graph optimization is also a maxima of posterior estimate, which is also a MAP. It only applied the assumption of system modeling and the Gaussian noise, meaning like the probability here, meaning F is likely will become an H, and W and V are Gaussian random noises. So because they are Gaussian random noises, so we can factorize all this stuff, all the probability here as a Gaussian distribution here, another Gaussian distribution here, and another Gaussian distribution here. So each Gaussian distribution is called as a vector of propagation, vector of update, and vector of priori vectors. And then we construct a graph to make all the states connected together. So we need to calculate its joint probability here. The joint probability, all the factors are connected together now. And then we try to find MAP, meaning that we need to maximize the probability here. Because these probability distributions are Gaussian distributions, so maximize probability equals to minimize the cost function over here. the cost function meaning this part inside the exponential, okay, this part inside the exponential. So it become minimize the cost function here. And how to minimize the cost functions over here is basically following a nonlinear least square iterations to obtain an optimal solution. In the other word, it is nonlinear optimizations. How we achieve to doing so is that in every state, you give an initial guess. Then by calculating the gradient, which is also known as a Jacobian matrix, by partial differential with the state, then you have the Jacobian matrix. After you got a Jacobian matrix, either you're using gradient descent, you're using Gaussian-Newtons, you're using LM method, you can get the increment. After you get an increment, this is your initial guess, and you pass the increment of according to the initial guess, then you have the first iterations. Then you do this iteration epoch-wise. In this epoch of data, you do it until the increment is small enough than some of the threshold, then you obtain your optimal solutions. This is how FGO difference with EKF. If we're looking at how this FGO can dealing with non-Gaussian error in this complex environments like this, first we need to give you a strong assumption is that we are assuming in the window it can be a batch from 0 to k. Good measurements are more than the bad measurements. Good measurements are more than the bad measurements. If this assumption can be valid, then these non-Gaussian factors cannot dominate the performance of FGO. Then FGO becomes stronger in guessing outlier measurement because the increased measurement redundancy make the estimation much more robust. Okay, so we have one example here for indoor positionings. So basically, we're using a UWB and an INS. So we have a drone. We have a UWB transceiver attached on the drone, and this IMU attached also on the drones. And then we set up an indoor environment like this. In this indoor environment, we set 6 of transmitter from A1 to 6, and we put this 2 part to generate a loss. And on top of that, we have Vicon to provide ground truth. And then we let this UAV trying to flying A patterns, Arabic number A patterns like this, and to collect the data. Okay, in this integrated navigation using FGO, we do 2 different types. The first type is that UWB already using nonlinear least square to come up with a position. So this is a positioning factors already here. So in the other word, it loosely coupled with the IMU pre-integration factor, loosely coupled integrations. In the same time, we also give the UWB raw data, which is ranging data, to construct a UWB range factors. So in the other word, we also do tightly coupled in this case. Then we construct the graph model, then we do nonlinear optimization that I mentioned earlier, then we're trying to obtain these navigation solutions. Okay, we do it in 2 scenarios. One is unlocked scenario, one is clean scenarios. And the update rate of the UWB is 5 Hertz and IMU is 200 Hertz. So this is the result in the clean environment. If you're looking at the loosely coupled FGO in EKF and tightly coupled EKF and FGO, the performance are quite similar because this is a clean environment. This is a clean environment. Just 1 centimeter differences doesn't mean anything. In the noise environment, which is loss and loss mix environment, we can see that the loosely coupled EKF comparing with loosely coupled FGO, there's a 20 centimeter improvement. And for tightly coupled, there's 10 centimeter improvement. And if you're looking at the ground truth over here, which is the pink color here, pattern 8, our tightly coupled FGO, the light blue one, is the most similar to the ground truth. So we believe that this FGO do have some robust estimation comparing to EKF. And the same conclusion can obtain in GNS-INC integration in outdoor. Okay, so we have a talk about to compare the GNS-INC integration of FGO and EKF. And if you're interested about the talk, you can find in the YouTube channel of ION, you can find the detail of this one. But the summary is the same, that both EKF and FGO, they apply the assumption in Gaussian noise. For FGO is less strict. And the assumption of first order macro chain, EKF have, FGO doesn't have. And FGO solved by iterative nonlinear optimization, while EKF doesn't have. So to conclude, the main differences is that FGO using batch data and you apply iterative optimization. So obviously the computational become expensive, and but it become more robust when the assumptions are violated. Now, okay, we have a good features to do integration now. The second question is, how do we select the positioning technologies? We have so many different technologies here. We have Wi-Fi, we have LiDAR, magnetometer, we have cell signal, we have GNSS, we have all the things. How do we select the positioning technology to help us to achieve this positioning? Okay, we are human beings, so based on the performance analysis and the limitation, we know what kind of position method should be good in different environments. So if you went to the keynote speech by Dr. Paul Groos, then we also agreed that the GNSS is very good at the suburban, and in downtown, if you have a 3DMA GNSS, this can also give a tick, depending on the availability of 3D model that you have in indoor environment. If you have the new receiver, a super correlation receiver, this one can put it into a question mark and even can get a good performance. And for cell signal, because it haven't widely deployed in the areas, so all the performance are quite put on a question mark. But we really hope that 5G and 6G can put a tick over here. For the visual positioning system in downtown area, it already performed quite good performance. Google already provide these services, but for indoor areas, because it doesn't have the map in indoor, so still a question mark here. In suburban, because there's low, the feature is also less comparing to downtown, so also put a question mark here. For Wi-Fi RTT or fingerprint, it already worked in indoor about 10 meters, but in downtown, we put a question mark because the density of a Wi-Fi station is not as much as in indoor. In suburban, it's definitely not work. Inertial system and PDR, and it should always be used. So based on this knowledge, if we can argue, okay, we based on heuristic knowledge, we select the right positioning method at the right time, and then we can consider this example of this positioning for urban life become like this. Okay, so when I work into the subway station using GNSS plus PDR, and working in the subway station, then it's Wi-Fi plus PDR in the map. I using in the subway, I using INS plus map to do map actions. Then when it comes to urban area to offices, I using VPF, VDMA, Wi-Fi, and PDR to solve the solutions. Okay, if we all know this perfectly, what to choose, what sensor at the right time, and we also make everything up perfect. What I mean everything here means is the model is linear. So the consider is a loosely coupled, so only identity matrix is used, completely a linear model. And the noise are white Gaussian, meaning I'm giving a zero mean. Then we simulate one data coming from area A to area D. Okay, so area A is open area, area B is urban Kenya, C is very deep, and D is a deep urban Kenya. So we give different technologies here. Like A, we give RTK, and we give zero mean and 10 centimeter accuracy in standard deviations. VDMA, we give 10 meters, and PDR, we will always get 0.8. Wi-Fi, we give 10 meters. And area C, because it's very deep, we only get 0.8. CDMA here, maybe in very deep, CDMA do better, so we give 5 meters. So we do all these simulations, but everything is perfect, meaning like the common filter know the noise perfectly, and these noise are white Gaussian noises. And I know what to change, what sense at what time. This is what we're trying to simulate. And then we give a different sensor frequency based on the real scenarios. So this is the data that we generate, okay? So let's looking at EKF, these common FGO when everything are perfect. When everything are perfect in the real-time processes, FGO, we talk about the forward solutions, everything is the same because both of them achieve MAP performances. Both of them achieve MAP performance. It means when you have the linear and Gaussian, EKF perform optimally. If you can afford to do the post-process, then a batch solution of FGO, meaning like a forward and backward EKF, can further suppress the errors. But what if one of the conditions is wrong? For example, it's not linear. It become a bit more non-linear. So what we do is that in our simulate data in area 8, it was an RTK solution. Now we change into a simulated ranging measurement with landmark. So as you can see here, we give different landmark and we give a ranging to increasing non-linearity of the solution or of the model, then see what EKF will do. We give quite a large initial guess, but a precise of the noise covariance, okay? So you can see clearly EKF taking 10 seconds to converge comparing to FGO. FGO can quickly converge because it do the epochwise iteration. However, EKF cannot. Then we need to talk about the second challenges of EKF is that EKF taking times to converge, making it a bit more difficult to achieve so-called a plug and play. I will talk about this term a bit more later. But plug plug and play, essentially meaning that when the new sensor comes, I'm just going to use it. I'm going to use it, and I want it perform perfectly, optimally in 1 second instantaneously. But EKF take time to converge, making it difficult. Sometimes it can be quickly converged. Sometimes it takes even long time to converge. So if we're looking at the conditions on how EKF can get a convergence, we get from the paper from Professor Krenner from 2003. That you have the three conditions. So basically, talk about the level of the non-linearity. If it's too high, it doesn't work. And if your second derivative of the model is bounded, then it's fine. So if your noise is non-Gaussian distributed, if the derivative of the noise distribution can still be bounded, then your EKF can still converge. Then you need to balance your initial guess and the non-linearity of your model. This is very important. If three conditions are achieved, then you can get a convergence. This is only the conditions, okay? This is only the conditions. But usually when we're doing a thin-list positioning, the noise are not Gaussian, or the noise are not Gaussian, but we still wish to using common filter, isn't it? So what we navigation engineer, we tend to use, especially for commercial solution, is that we tend to overbound the noise, which is we tend to overbound the R to gain the robustness. We don't want our solution to go crazy, right? Solution is not good is one thing, but we don't want our solution to go crazy. So if we want to overbound the noise to gain the robustness, what performance we will get? This is a previous result that we have a large initial guess and the precise R. So when we give an overbounded R in here, the case we get multiply 1,000, a scaling factor of 1,000, then you can see the conversion time is from 0 seconds to from 10 seconds all the way to about 30 seconds. And this is theoretically proven it is correct, is that the EKF convergence rate is related to R. If you can refer to the paper here published in 1997, it mentioned that a very high value of R lead to very slow convergence rate. So you must do a very good trade-off between the stability and rate of the convergence. So what does it mean to navigation engineering like us? It means it's always very painful to turn an EKF because you always need to find different user case to find the best turnings to do a perfect EKF, which is very, very difficult. So in our commercial solution, what we usually see is we don't want nonlinearity. We're always using loosely coupled as a solution because it is robust, but the accuracy now become compromised. Why it is compromised? The reason here is because the redundancy of the measurement, this is very important keyword, the redundancy of the measurement did not fully exploit it in the estimations. I'll give you one example in the GNSS-INS integration that I mentioned that we published earlier last year. This is the paper for GNSS-INS integration. If you're looking at the loosely coupled EKF, the result is about 9 meters in mean. If we're looking at the tightly coupled EKF, the result is about 8 meters. Slightly improved, but not too much. But you can still improve about 1 meter. So we can argue that, okay, I still want a tightly coupled. But why this is only 8 meters instead of like a lot? Because this nonlinearity in the tightly coupled actually pose challenges for EKF, especially when you have more sexualizing views. So if you're using an FGO, comparing to an FGO, you can solve the nonlinearity in the epoch-wise integration. Then you see when you come in from the loosely coupled FGO, it was 7 meters, but now you come to tightly coupled FGO, now it becomes 3.6 meters. So FGO can enjoy the benefit of tightly coupled, which is redundancy of the measurements comparing to EKF. So this is, and it is also very good for plug and play. I'm definitely not the first one to talk about this. In fact, this is back to 2014. There, Dr. Chu from MIT Computer Science and Artificial Intelligence Lab, they have a project for all source navigations, source positioning and navigation. I highly recommend you guys to read the project and read his paper. Very, very interesting. So he argued that using a FGO, we can achieve a plug and play, even the nonlinearity is high, because and make the convergence become faster. So if we have a cost function like this, between epoch 1 and epoch 2, we have the basic dynamic model. We have one cost. When you have a different model coming in, you have a PDR model for in-betweens, and you have the Wi-Fi measurement models. Then you can just simply add 2 cost functions into these objective functions. And when you have a VPS coming in, if these images, the visual map, you basically just add one more factors in this optimization platform, so it can really achieve a plug and play. So what is even stronger is that when we're dealing with, for example, this XK, the current epoch time, but when we know there is a time delay measurement coming in, it can still consider this time delay, which is the latency measurements in the optimizations. So it also make use of those measurements that come late because of communication delay. So this is also another benefit of it. But when we do FGO, one of the biggest problems is that when the batch become really big, for example, from epoch 1 to epoch 100, epoch 1000, epoch 10,000, the computation load will go crazy. But don't worry about this, because there's a research team in robotic field. They already developed something called marginalizations and incremental smoothing to make sure that you have a time window and they can still make your batch optimization can be done in real time. If you are interested, please go refer these two papers list over here. Right. So this is about FGO. So FGO, I think, is perfect to do a plug and play synthesis positioning if your devices can accept a bit more of a higher computation load. Now, the next question is, can we automatically select the right sensor at the right time? Previously, we select the sensor based on our human knowledge heuristically, but is it possible we can choose the sensor automatically at the right time? Again, Dr. Chu, they also come up with one solution. At that time, their solutions is military applications. You've come from the seagull, then you have different sensors, and then you go to the land, then go into the urban. They have a whole bunch of different sensors over here, which I believe is very similar to our IPI and commercial context here. So in his paper, they published in IEEE IQAR 2014, how to they select the best set of sensors like this. They define the sensor set by the heuristic rule. For example, PDR must be used, INS must be used, and if GPS give a higher weighting because it's absolute characteristic. And if you have visions, then probably you don't need the other odometers, stuff like that. They define the sensor set by heuristic rule first. Then they're trying to predict the positioning accuracy of each sensor. When they say predict, is estimate. They estimate the positioning accuracy. Then they find the observability of different model set, of a different sensor set. They choose a different set of sensor and looking at observability. Then they find the set of sensor with the optimal observability as the final solutions to achieve the optimal synthesis solutions. If you're looking at the equation, it's like this. It's like this. This is a very typical measurements to state the models, and we have measurement model G. It's also known as a Jacobi matrix if we're talking about the estimation algorithms. Then we're doing the least squared and do the pseudo inverse, making G looking like this, and this is our measurements, and this is our state. This is error state, of course. So in here, by looking at the Jacobian part, this part, so this H, blue matrix H here is actually representing all the constraints from all measurements to each of the state. Okay, so it means this means the model observability is inside this edge. In order to identify different direction of the constraint that are orthogonal, and they have a different amplitude to represent it. We're doing SVD to finding out all the eigenvalue, which is using to represent the amplitude, of each direction of the constraint. Okay, so what is the good estimation is that even the directions with the minima amplitude, meaning that the direction that your model give a minima constraints, you can still provide a certain level of constraints, certain level of performance, then it's a good observability. So in their field, usually they're just using a predetermined threshold. If your minimized eigenvalue is larger than that threshold, then your observability is guaranteed. This is how they choose the ultimate subset of sensors. But is this perfect? Could this have any problems? I will argue that yes. When you violation the assumption met, what is the assumption met that could be violated? So this looking at if we're going to predict the sensor positioning performance by state estimation algorithm, which is what I mentioned earlier in the previous page. The pros, obviously, you know what exactly happened in the estimation, so you can represent it quite clearly. But what is the cons? The cons is that when your measurement use are mostly unhealthy, then it may violate your assumption already. And the second violation of assumption could be, okay, your noise covariance, no matter in EKF we call it R, in FGO we call it information matrix, this sigma. If it cannot reflect the actual qualities, then your predicted sensor performance will, by state estimation, cannot really represent the real situation. So that's the problem. That's the problem. So what we argue here is, okay, can we try to using another method? In here, we put artificial intelligence as another method to monitor the predicted sensor position performance. Why? Why is this? The advantage here is that AI, they can use information. They are not used directly in the estimation, but somehow related to the sensor performance. Here somehow means this cannot be represented by a math, but it is related to the performance. For example, the dynamic object in the environment to avoid to make your visual autometry become worse, dynamic object to generate multipass for your signal. This is very difficult to model by math. So, but AI, they can include these kind of informations into consideration to monitor the positioning error. In the same time, it can still consider the estimation processes like models observability that we mentioned earlier, pseudo range residual, these kind of indicators that generate from estimation, they can also consider. But what's the problems? The problem is we are very hard to know what exactly happened in the network. We don't know what exactly happened. Of course, in terms of the weightings and all the stuff, we know the math there, but we don't know what the math represents. So we don't know what happened. And it's very hard to monitor and validate its performance again. It's very hard. But this comes to a problem is that, okay, so who we are going to monitor AI is similar to who is the auditors. Like in our real life, auditor is going to audit some of the companies, some of the institution, but who is the auditor of the auditors? So this is a philosophical problem that we always need an auditor for the auditors. So in this, I argue that if this state estimation is the systems, then we're using AI to audit the state estimations. That's why we're trying to argue here. So we believe that this should be intelligent integrated navigation solutions. Here, the intelligence, what I mean is that the ability to acquire knowledge and apply the skills. So the knowledge here is environment, for example, a suburban, downtown, and indoor areas. And the skill is like a state-of-the-art positioning method. We can have a GNSS RTK, 3DMA GNSS, VPS, Wi-Fi fingerprint. So we believe that artificial intelligence should play a part in the integrated navigation system. Again, I'm definitely not the first one who is advocating this. In fact, I'm not, but Dr. Paul Gross is actually talking about this in 2013. I will give you the slide very soon. Okay, so what I propose here is that deep learning models can be used to predict the environment and sensor noise for an integrated navigation solutions. We can use raw data from all the different sensors, and we can also include other information like the map such. And then the first layers, hierarchically speaking, the first layer could be the context, whether it is open sky or it is urban, you're driving or you're working, we can do the context awareness. Then the second layer is that we select the good sensors, different sensor, we give different sensor a different weighting, which is meaning we give a different scaling factor in front of the information matches. And then, if possible, can we try to also estimate the noise of the measurements? If we can do so, then we can come up with intelligent adaptive noise covariance for integrated navigation systems. That's the visions to be done, but a lot of scientific problems need to be tackled to achieve this. Like I said, I'm definitely not the first one who bring this idea. In fact, Dr. Paul Gross in 2013 already advocated this. He said that we can use in sensors, radios, and different database to do context detection and determinations. And based on the context, we give the context-dependent navigation algorithm to achieve the so-called context adaptive navigations. So this idea is already been discussed in 2013. So it's about 10 years now. So I think we should start doing something about this. So I give you one example about content awareness on indoor and outdoor. We take one data in Hong Kong Polytechnic University, our campus. We collect data at 4 different places, like a relative open sky, half open sky, intermediate areas, and this is very deep intermediate areas. We can still see some sky, but there's some head over here to block some signals, and very deep indoors. And then we're using a smartphone with a 4 constellation of the GNSS to receive the signals. So as you can see, this is time, and different color means different data that we collect at different areas. As you can see, that it's quite clear that in outdoor, the number of satellite available is a lot. Then in the intermediate slide indoor, it's like this. Then when you go to deeper area, it's like this. When you go to real indoor, blocking all the signals, almost no signal received. So this can be a rough indicator whether you are indoor or outdoor. And I believe this is been using in your smartphone or watches to determine whether this is indoor or outdoor. But it's difficult to say something like this. What is indoor? What is outdoor? This is our polio compass. You can see like this part, is it indoor, or like this is indoor? This is indoor or outdoor, or only this side indoor, or this second floor is indoor. So hard to define what is indoor, what is outdoor, which is a common problem for us. But what I'm trying to mention here is we want to separate what is indoor, what is outdoor. We want to separate a place that GNSS is good or GNSS is bad. Okay, we want to separate a place GNSS is good or GNSS is bad. So one method I believe maybe it can help, which is coming from a work from our group, is that can we try to define the outdoor by GNSS positioning arrow that mainly come from a multipass and loss, come from multipass and loss. So this is an example of it. So this is an area close to our campus, and the color here representing the positioning arrow, the positioning arrow caused by multipass and loss in this area. Blue means almost no, and red means a lot of arrows, and we are checking a different height. As you can see, as the height going more higher than all the flow, then there's no positioning arrow. But when the height is low, you can see different area have a different positioning arrow. So maybe we can use these positioning arrows to define the outdoor. But how we generate this this positioning arrow may caused by multipass is like this. Okay, so if we have a satellite in famous, we know where the satellite is. We have 3D model. We can conduct this ray tracing. So the map is really useful. We can do the ray tracing algorithm, and we come up with the predict range. Then we can apply the d-square positioning method to come up with the estimate position and compare with true position. Their difference become the positioning arrow. That positioning arrow become a color here. So we can generate a wide areas of GNSS positioning arrow caused by multipass and loss. So this may be one method we are arguing. And I also want to mention that machine learning in GNSS is actually a quite hot topic in terms of dealing with unloss and multipass. And in fact, the first paper is using in 2005 is using a neural network to deal with that. It's Italian teams, and since 2018, there are more people utilize deep learning to dealing with unloss and multipass. As you can see, this is the number of papers that we see in ION database, depending on the year. So deep learning is starting to use to detect, classify, or even correct unloss measurements. So I'm going to show you one case where deep learning is possible to correct unloss measurements here. So this is based on my students, who now is a postdoc researchers in Hong Kong Polytechnic University, Zhang Guohao. So he published the paper in 2021 in IEEE Census Journals. So using a deep learning models to predict the GNSS pseudo-range error in urban. So how to read these figures like this? This S is the different number of satellites. You can study a satellite index, and this S is the data index, okay, depending on the time domains. And the y-axis is the ranging arrow, is end ranging arrows, and the blue color here is the real pseudo-range arrow that we calculate from the ground truth, and the red one is the predicted arrows pseudo-range arrow from the deep learning network. If you take a closed loop of this, you can see that the deep learning actually really trying to find out the arrow of pseudo-range quite accurately. It's quite accurately in many of the place. If we're trying to quantify what happened in this data, is that, okay, when there is not applying the deep learning corrections, if it's loss scenario, it's about 3.7, and loss scenario is about 18.7. The combined all is about 7.3. But after we applying the correction determined by the deep learnings, it didn't affect our loss measurements. The clean measurement is unaffected. That's why I want to emphasize. For the pseudo range one, it becomes from 18 to 8, making all the measurements means reduced to around 5 meters. So this is just one example. Of course, there are some in-sample or out-of-sample testing validation issue that generally we observe in deep learning research. But here it's giving you one idea that deep learning might work. We should open up the mind to look at these solutions for our urban navigations. Right. So we also apply this deep learning method, to using a full network in our previous experiment of UWB and INS in that indoor experiment. And here we are not to correct, but what we do is using the predicted noise as noise covariance and put it into graph for optimizations. So in the other word, we're trying to using the deep learning network to adaptively turn the noise variance here and to provide adaptive optimizations. Okay. So here's the performance. Looking at on the left-hand side here, this is the actual measurement error. Again, we derive from the ground truth. This is in the ranging domain. This is in the ranging domain. Different row means different transmitter. We have 6 transmitter here. Okay, we have 6 transmitter here, and this one is no error because we put on the high on the sky, so there's almost no multipass there. So this is the predicted measurement noise by the proposed deep learning network. You can see that it's quite similar. The trend is quite similar in a way, It's quite similar in the weight. And for this very clean one, you see the scale here is 0.3 and 0 means all are very small. So you can also find out it's quite clean. And for this part, you also finding out there is a problem here. So if we apply this into the factor graph optimization, the result is this blue one, adaptive FGO with deep learning network. So comparing with the ground truth here, you can see the trajectory is very, very close to the ground truth. And this is the 2D arrow. You can see again, the trajectory is very close to the ground truth. And statistically, the mean is about 13 centimeters and standard deviation is about 6 centimeters. So we argue that AI plus FGO work the best for this case, and it might have a lot of potential later. But if you're looking at here, we're trying 0.4, 0.6, 0.8, meaning that we're turning the scaling factors between IMUs and INS. It doesn't really work. You can see no matter how we turn the scaling factor between IMU and INS, it doesn't really work. So you do have to go to the measurement level to have adaptive noise that you can achieve the best performance. Okay, so I'm very, very close to the conclusions. So I believe that existing area for navigation is always like this. We have to use using AI and to help remote sensing to generate a map. And the map is help us to do navigations, and we're using our smartphone according to the map to do navigation by our human beings. But now I argue that we're starting to think about advanced sensor integrations. It can be hybridizations in IBIM field, and to dealing with the complex environment. And we may studying a new applied science areas, which is to do thing understanding, adaptive noise turning, even measurement corrections to help our advanced sensor integration algorithm to achieve the best performance. And then this best performance may be helped to cloud sourcing data update. And this cloud sourcing data update may come up with the map, which can use to turn the hyperparameter of the modeling. I believe this blue, red, and green are the new applied science area for our IPIN to achieve indoor positioning and indoor navigation ubiquitously. That's our goal. So here comes to my conclusions. So since this positioning require a plug and play filter platform to integrate measurement from different sensors, it will be best to do it tightly. And EKF can also achieve plug and play if the integration model are linear and noise are Gaussian distributed and initial gains are sufficiently good, I should say so. But FGO using batch measurements and epoch-wise iteration to alleviate the challenge of nonlinearity and non-Gaussian. Then to select the right sensors at the right times, AI and map might help. How to design a network to serve for the purpose is the new area for us to research. Finally, I want to respond to the new channel that we have in IPI community, which is wonderful. I believe this is really the time to IPI to do interdisciplinary computer science, geospatial, aerospace, robotics, electrical engineering. We should work together to achieve this positioning altogether. And thank you very much for your attention. Questions, comments, and collaborations are welcome. Thank you.
Okay, thank you, Dr. Xi. Thank you for your excellent report. I believe your report has a very wide audience, so maybe we have many questions from the audience.
Yes.
Okay, we have one question from
yes, I think
from Professor Paul Graves. You can see the problem. Yes. Okay.
Yeah. So Paul, thank you for your question. So for like UKF and particle filters, let's talk about authentic UKF and iterative KF. In fact, they can achieve quite a bit similarly to FGO. So let's look at the comparison here. Let me bring to that page. Excuse me. Let me. Sorry. They can achieve quite similarly in a way, but it cannot really replace in the FGO. Let me show you this page first. So we conclude here that the main differences here is using batch data and iterative optimizations. Okay, so if your common filter consider multiple time epochs, for example, epoch k to equal k minus n, multiple time epoch, it can also serve as a time window, similar to a batch. Here we use in FGO, but the difference is that EKF they marginalize is not as good. It's not as good as FGO because the reason here is because the nonlinearity of the models. Because in common filters, you only do the recursive one, right? So when you're trying to linearize nonlinearity, it's not as good. But someone may argue, okay, now how about I do multiple epoch EKF, then also do iteration inside the EKF, where you achieve similar performance as FGO. We tried it, and we can also say yes. So it's not necessary to really apply this FGO. The important message here is to consider a more window of data, because they can bring you the more data redundancy, and then trying to apply epoch-wise iterations to solve the nonlinearity problem so that you can enjoy the benefit for tightly coupled. As for the unscented part, for the particle filter part, sorry, Paul, I don't know how to answer your questions. I may need to read a little bit more. Hope it's fine.
Okay. Dr. Paul, do you have any comment?
We have a second question from Sataki Ogizo.
Yes. Can you hear me?
Yes.
Thank you. Thank you very much. Very interesting. I would like to ask you about the limit of the FGO, because I think FGO is very difficult to adapt to a large-scale data, such as day-long measurement, because there would be many local minima in that optimization. So do you know any solution for that?
Yes, that solution for that is there's two. It's quite popular. It's also not developed by myself, by the robotics communities. One is called marginalizations, and one is called incremental smoothing and mapping using Bayes trees. So the rough idea is also to trying to make those filter out. For example, if this is your window, this is your window. Those being filtered out is trying to represent as a priority factors inside your graph, and trying to also similar to common filter to let this filter out measurements to be a priority factor of your graph, so that to make sure your window still can achieve the real-time performance. And in the incremental smoothing and mapping, they are also confirmed that even you have something like a loop closure constraint, which is a very strong constraint, less kind of very nonlinearity, very strong one, it can still achieve. So I recommend you to look at these two papers. Marginalization to achieve sliding window, which is this one. You see, they're trying to achieve the planetary landing. So computation load is a big problem. And the second one is from CMU, from Michaels and also from Frank.
Thank you very much.
Thank you. Thank you for your questions.
Is there a mechanism to dynamically adjust the window of the vector?
Yeah, so that's down to my suggestions on how machine learning can help us.
Okay.
Yeah, there are also, let me add a little bit, sorry. So there are people also using so in fact there's just two ways. In fact, it's just two ways to determine the window size, which is these two ways. You can use state estimation again to looking at the window size to find the ultimate observability. You can do that. You can, based on your residual, you can do that. But again, it doesn't solve this problem here. Using AI then is another problem, right? So we don't know how to design a good network. So it's still very open questions, I would say, Professor Wei. Yeah.
Okay. And page 41, you mentioned you use machine learning to predict n-loss. Yeah.
Yes.
So my question is, you just recognize n-loss and remove the measurement, or you can correct it?
We can correct it. We can correct it. In fact, we can apply corrections to it. And I do know in indoor positioning scenario, someone also doing this n-loss delay estimation and also correct it. So it can be done. It can be done.
Okay. So any other questions from the audience? We have, in fact, we have 5 minutes.
Yeah, I probably do a bit too fast.
Let me check whether there are question from the live broadcast channel.
Paul has
yeah. Dr. Paul?
You mute yourself.
Oops. Okay. So I'm thinking in terms of the non-Gaussian problem.
Yes.
So I think a number of people have demonstrated that non-line of sight measurements have a skewed distribution. So the basic factor graph algorithm seems to assume Gaussian distributions.
Yes.
So that you can work with the logarithm of the PDF.
Yes.
So is there a way of dealing with these skew Gaussian distributions using that same approach?
Yes. In fact, the answer is yes. So skew distribution is a kind of distribution can be modeled by different distributions. The distributions that is quite popular in robotics field is called GMM, Gaussian mixture models. So one of our paper is to adaptively. So this is working with Tim Pfeiffer from Chemnitz University in Germany. Is that we also adaptively estimate the weightings and the mean and the standard deviations of the GMM model, which is 9 parameters there, using a batch window of the residuals. So now the second question now is, okay, even if I can estimate, if it is not a Gaussian level, I cannot come in from this max to this minimum, right? So in fact, you can still make it as a minimum. It's just that your cost function is extremely complicated. It's not as clean as like this. You have a lot of exponential, a lot of stuff there, a linear combination of a lot of exponential stuff. So if you just simply applied the nonlinear optimization here, it means that to solve these Jacobians and this Herschel matches become very difficult. But we are lucky because there are a lot of university and very big entity like Google. They also provide a solver to help us automatically derive those very complicated Jacobian matrices. So even if it's a linear combination of exponentials here, we can still derive. And our result also shows the same. But the problem is that if you have a GNN model, you have 9 parameters using 3 Gaussian 2 model, 9 parameters, then you got more uncertainties. Your model observability will increase. And it also comes to a problem that your window size, is it the same skew or it's not a skew? Is it this part of same skew or it's not a part of same skew? So the window size selection problem mentioned by Professor Wei is still there. So you cannot solve all the problem.
Okay, is the time for me to ask another question?
Yes, of course.
Okay, great. So one advantage of the batch factor graph approach is that you can do outlier detection over multiple epochs,
yes,
rather than only looking for outliers at the current epoch. Have you tried that?
Can you say again?
Have you tried outlier detection over multiple epochs together?
Yes, yeah. In fact, yes, we do. First comment is when you do FDE in FGO, then the computation loads will go crazy. That's the first thing. The second thing is that when the batch to exclude when we do a detection, okay, that's so-called consistency check. If your thresholds is manually select For example, no matter how many states I'm observing, how many measurements I have, I just give it a 10 meters as a heuristic one. Then it works. But the problem is when you're trying to do integrity monitoring, that you have all these states and the degree of freedom stuff, then you need to apply those threshold there. You come in as a huge threshold. It doesn't mean anything to the integrity monitoring. So that's another problem we are tackling now. But to answer your question, it works, yeah.
Another question? Okay.
Can I ask?
Yeah, go ahead.
Yes.
Okay, thank you. I have a question about the comparison between the FGO and particle smoothers, because I think the non-Gaussian assumption is very similar to the particle smoothers. But yeah. I personally do not go for the particle smoothers. But what do you think about the difference between particle graph optimization and particle smoothers?
Yeah, I think particle filters or particle smoother, what they do is, as you mentioned, to dealing with the non-linearity, is instead of just using one state, right? Using several different states to find out the model. So it solved the part of non-linearity, but it didn't serve the part for multiple measurements. So again, if you're using a batch particle filter, that could also be similar with FGO. That's what I believe. Yeah.
Okay, thank you.
Thank you.
Okay, because of time, we must end this session. It seems, Dr. Xu, you are very familiar with online teaching. For example, writing user mouse, maybe because of COVID-19, I think, yeah.
I could bet over us art. Yeah.
Okay. Thank you again. Thank you for your excellent report. Let's move to the next session. It's the parallel session.
Thank you.
Okay.
See you guys.
Thank you. Bye.
Bye, Paul. Bye.